Okay, so we left off. So let me get a couple things out of the way. So we've got the connect page here. You've got that kind of fifth Excel and connect. After today, you should have everything you need to kind of work through those completely. We've already covered a lot of it. If we look at the files, we've kind of got our final exam practice materials. I updated that formula sheet to have a couple formulas that didn't carry over on there when I uploaded it. Then you have the 2 practice exams, and then in the in-class data, this linear regression files, we'll be working off a couple of these, right? So today we'll mainly focus using this GPA data. We did a little bit of work on it last class, but we'll add some more stuff in today. So where we left off, if I remember correctly, was, remind me, did we look at these regressions, right? Yeah, we went to smoking, birth weight. I show you some stuff on the GPA. And then I started mentioning, so we had these formulas I showed you. What I wanted to get to was that we left off saying, well, look, I can run a simple linear regression where I've got one variable on that right-hand side, right? But it's probably going to be that when I'm trying to predict this Y value, a lot of other things matter as well. So I probably want to, if I'm trying to predict income, I probably don't just want years of education. I probably want the person's age. I probably want to know, what their job title is. Like I might have all this other information that's going to be really helpful at predicting incomes that I want to use. Right? So you can kind of think about, let's say I had a crime equation. Right? What ends up being true is if I were to run this regression, and let's say I just had police force expenditures, so how much money was being spent on the police, and the crime rates, and this could be at the county level or at the state level, what's going to end up being true is I find a positive coefficient. And that doesn't really make a lot of sense because if I spend more on my police force, why would crime rates be going up? Well, it's probably because I have to spend money on my police force because there's other things that are creating crime, right? So if I don't include those other variables, my coefficient on this police force expenditures picks up all those other effects. So if I just simply include unemployment as well, well, now this unemployment variable kind of captures that when economic conditions aren't good, right? When unemployment is high, right? That potentially crime is also going to be high. But as soon as I include this in my regression, my police expenditure coefficient no longer picks up the effects of whatever variables that I am now including. So when I wasn't including them in the regression, that coefficient was picking up not just the effects of police force expenditures, but all other things that I left out of my regression that are also correlated with police force expenditures. Okay. So that's the general idea of what we're doing, is we're trying to include more variables that help us better predict our Y variable. Okay. So if we think about, what this really becomes is I'm still trying to choose this line of best fit. Remember we said we want this line of best fit such that we're minimizing the amount of errors we're making. Right? So if I go back, right, we had the errors, right, from our predicted Y and the actual Y, and we were trying to get this line of best fit that minimized the sum of those errors squared. Well, now when we include additional control variables or additional right-hand side or X variables, well, now I've got this equation, I'm trying to minimize it, so I take a derivative in respect to not just the intercept and the slope coefficient, but the intercept, the first slope coefficient, the second slope coefficient, right? Each one of these variables has a slope coefficient associated with it, which is telling you the relationship between whatever your first X variable is and the Y variable. Then B2 is the relationship between your second X variable and the Y variable. B3 would be the relationship between the third X variable and your Y, so on and so forth. So however many X or right-hand side or independent variables that I include in my regression, I'm now going to have n equations and n unknowns that I can solve for. So the math becomes a little bit more complex, right? If I go back to here, I had the equation that I know, like once I had those 2 equations and 2 unknowns, here's how I can find the slope intercept coefficient. Now when I have n equations, n unknowns, these equations just become more complicated. So it's a little bit outside the scope of this class, but if you want to, take a look at, if you've taken some linear algebra or you have some advanced calculus, this has a kind of nice walkthrough of how you actually would solve those n equations and unknowns. But ultimately, it doesn't matter because Excel can do it for us, and the interpretation of our coefficients really barely changes. So before we said the way that we interpret a slope coefficient, right, one of those coefficient values we saw in Excel, it was a 1 unit change in x would cause the predicted y to change by whatever that coefficient is. It's still the same interpretation. It's just now we add on holding everything else in the regression constant. So if we go back to that crime equation, now the interpretation of our police force expenditure would be if I spend $1 more on my police force, beta 1 is the predicted change in crime from that $1 increase, holding constant the unemployment rate. So holding constant everything else on the right-hand side. So we'll get some more interpretation examples that I think are make a little more sense here in a second. But that's basically the interpretation hasn't changed other than we have to add on holding all else constant to the end. For the intercept, it's going to be very similar as well. So now for the intercept, it's just the intercept is the predicted y value, not just if the one x variable is equal to 0, but if all the x variables are equal to 0 now. Right? So same kind of interpretation, so it's slightly different when we have more variables going on. And as we work through some examples in Excel, I think it'll help make a little bit more sense. So we don't have to worry too much about the math solution because Excel will do this for us. So come back to the R squared in a second. And I'm going to touch on this idea of causation and correlation. So let's go to that GPA data. We had the regression we ran from last class, so I'm going to rename this. That was 421. And I'm going to go back to the original data. So it looks like I have to scroll up here. So I had all this information on SAT scores and about these different students, and I also had their GPA. So what I do for right now is I'm going to insert a row. I'm going to move this athlete variable over here, and I'll kind of show you why here in a second. And I'm also just going to move this SAT squared out of the way because we're not going to use that. And then I'm going to move everything so that we can kind of see it. So I'm just moving, get SAT score out of there, delete this row. Here's my kind of data that I'm going to work with. So I might be interested in something like, how does being a student athlete impact college GPAs? So let me switch over to the .cam here. Taking a second. So what I'm thinking about is I want to run this regression because I'm interested in how do GPAs, right? How are they related to whether or not the individual is a student athlete? So here, kind of like the smoking variable example I think we looked at last class where the mother's smoking, athlete is a 1 if they're a student athlete, 0 if they're not. So the interpretation now becomes a 1 unit increase, well, is just going from a 0 to 1. So being a student athlete relative to not being a student athlete, here's the predicted change in GPA. Right? So I'm going to go ahead and I'm going to go to my data tab. I'm going to go to data analysis, move down here to regression. My Y variable is college GPAs, right? That's my left-hand side variable. Control Shift or Command Shift on a Mac and hit the down arrow to quickly select that. And then my X variable, go up here, is being a student athlete. So I'm going to select that variable. I selected the labels, I hit OK. I get my regression output. I'm going to zoom in so we can see it. And so what it looks like is being a student athlete relative to not, right, that 1 unit increase, here it says just a 0, 1 variable, so going from the 0 group to the 1 group, being a student athlete would predict that GPAs for that individual be about 0.28 lower. So, and the p-value here is pretty much 0, right? E to the -9 means move the decimal point 9 places to the left. I've got a p-value of pretty much 0. So if I only reject when the p-value is less than alpha, Well, with a p-value of 0, I can reject at all levels here, right? And what am I rejecting, just as kind of a reminder, what I'm rejecting is that we always have the null, which is that slope coefficient is equal to 0, because we're trying to find whether or not it's not equal to 0, right? We're trying to see if there's a relationship between GPA and being a student athlete. So we stack the deck against ourselves. We start out assuming there is no relationship. Well, our p-value 0, we can reject the null. So we're rejecting that there's no relationship, or that we found evidence of that there is a strong relationship between these two things. Okay? There's a strong correlation, so to speak. Okay. So I'm just going to rename this one as naive, right? Because it's naive to think, well, I'll leave this up here, that being a student athlete is the only thing that matters. And in fact, if we have a data set and we have primarily D1 Division I programs, you know, their men's basketball and football programs might be a little bit more lenient on the academic standards of athletes. So maybe, you know, the intellectual ability of this student athletes varies from the general population. Who knows, right? So what we could then think about is, okay, what if I know that being a student athlete might be correlated with academic or intellectual kind of ability. So I'm going to actually try to measure that so I can hold that constant. So now the interpretation would be holding constant the SAT score of the individual. So the thought experiment is, if I had two individuals, when I'm saying holding constant, two individuals with the same SAT score, but one of them is a student athlete, here's the predicted change in their GPA now. Before, we didn't have any, you know, measure or control for what their kind of academic quality or intellectual ability was. So now, go back to our original data. Scroll to the top so we can just see what I'm doing. Go to data analysis. I'm going to leave my, my y variable hasn't changed, but for my x variable, I'm going to select SAT score and whether or not they're a student athlete. Once again, Control Shift or Command Shift and the down arrow selects both of those variables for me now. And now I get regression output that has multiple right-hand side, multiple independent or multiple x variables in. So now if I look at the coefficient on athlete, well, before it was negative 0.28, now it's only negative 0.05. And not only is it negative 0.05, my p-value is 0.25, so I can't reject the null. If I can't reject the null, what I'm saying is, yeah, that true relationship could be 0. Being a student athlete could have no impact on the GPA if I can hold constant what the individual's SAT score is, right? So two individuals with the same SAT score, we would now predict that if one of them was an athlete and the other wasn't, the athlete would have about a 0.05 GPA, or lower GPA, but we can't actually say that it would be statistically any lower, right? Because we can't actually say that that coefficient is any different from 0, because we're just basing this off of a sample, right? Any questions at this point before we kind of keep moving here? Okay. So, this might not seem like it's really powerful, but whenever we have variables, like we're looking for the relationship between student athlete and GPA, if there's other important variables that we're omitting, it's going to mess with this coefficient. Notice this looked like it was negative. Well, that's probably because being a student athlete, there is a correlation with what your SAT score is, right? So we started off thinking, hey, it's really bad to be a student athlete. Now we think maybe it doesn't matter, right? And the whole kind of motivation behind this might have been something like, being a student athlete, it's going to take a lot of your time. So maybe it has a negative impact. But, maybe it teaches you time management skills and, make sure that you're a little more attentive to your grades. So who knows, maybe it has a positive effect. Well, when I include SAT, that's good. I'm starting to control for more things. But if I go back, and we'll call it this one, naive 2, right? Well, if I go back and I look at my data, I'm like, well, man, yeah, I can control for the SAT score, but I got a lot of other information that probably helps me predict GPAs as well. I've got their scores on some verbal math tests. I've got their rank in high school. I've got some demographic information. So what I'm going to do is what we sometimes call throwing the kitchen sink at it, right? So I've got my college GPA. For my X variables now, I'm just going to include all these, right? Why not? I've got the data, right? I think they all probably have an influence. So now, when I include all of these X variables or right-hand side or independent variables, now think about it. If I have more information about the person, I should be able to come up with a better prediction for GPA, right? Because I now am not predicting GPA just based off of 2 things, but I'm predicting it based off of a ton of different things, right? Okay, so I now look at my athlete variable, and now it looks like, well, if I can hold all these other things constant. So the thought experiment is 2 people with the same SAT score, same high school rank, they score the same on this verbal math test. They're either both male or both female. They're either both white or they're both black. They have the same total credit hours. They went to a high school of the same size, but one of them, right, we're holding everything else constant, but one of them is a student athlete, right? That 1 unit increase going from a 0 to a 1, the predicted increase of that student athlete, or sorry, the predicted increase in GPA of that student athlete would be 0.17, right? And the p-value is pretty much 0, so that's a statistically significant effect at any alpha that we're looking at, right? Any level of significance we want. So we can control for more factors. We just get a more accurate depiction of what the relationship is between the variable we're interested in, being a student athlete, and that Y variable GPA. Okay? You can kind of think about, what if we had, what if I tried to interpret this SAT score variable? Well, then the idea there is 2 individuals who are either both athletes or both not. They have the same high school rank, same score on this test, etc. Right? All this other stuff is identical for these 2 individuals. But one of them scores 1 more unit, right, or 1 point higher on the SAT score, then their predicted GPA would go up by 0.001. And that's pretty significant, right? E to the negative 117, that's a p-value of 0. Okay? Any questions on that idea? Okay with that? All right, so we'll go throw this over here, and I'll call this, I don't know, kitchen sink, right? We threw everything at it. We threw everything we had on our data set. So the next thing that we're going to talk about is R squared, okay? Well, actually, I'll come back to R squared because I think I have some causation stuff and kind of come back to looking at Excel in a second. So we'll skip over this for a second because I didn't really focus a lot on that example, and I kind of already discussed it a little bit. But let's think more about last class we had a regression where we were looking at birth weights and then whether or not the mother smoked while pregnant. So this is a good one to get at this idea of correlation versus causation. So when we're looking at these coefficients, it's really easy the way we speak to talk about them as though they're causal. But like when I'm saying, if being a student athlete predicts that GPA is this much higher, well, it's that it's correlated on average based off of the sample data we had that we would see the GPA be that much higher. So when I'm thinking about the interpretation here on this, does the mother smoke while pregnant variable, this is the predicted change in birth weight if the mother smokes while pregnant, but we're not holding anything else constant. So we definitely, if you run this regression, I'll show you some results last class. I mean, you'll definitely find a negative coefficient here. And it actually is pretty large. But then you have to start asking yourself, okay, that's just correlation. It's not that smoking while pregnant necessarily decreases birth weight by whatever I'm seeing, because there's a lot of other variables that are important that I didn't include in my regression. So the example I would give is, if we look at the data, who do you think is kind of more likely to be someone who smokes while pregnant? It tends to be people with lower education levels, right? If we have some measure of their education, and if we have measures of income levels or socioeconomic status, lower income levels tend to be correlated with being more likely to smoke while pregnant. Well, it's correlated with being more likely to smoke while pregnant, and we know the impacts of having less money on birth weights is also, the less money I have, the more birth weights go down because I don't have access to as high quality foods, healthcare, etc. So if I don't include any, control for income or education, this coefficient on the mother's smoking variable is going to pick up those impacts as well. So it's going to be like inflated, right? It's going to be, look, you're never going to see like with the student athlete variable where the sign flipped as we included more controls. But it may not be quite as large of a negative value here when we're looking at does the mother, when we're looking at what's the impact on birth weights of the mother smoking while pregnant. So that's the idea of correlation versus causation, that if we haven't controlled for every other factor, it's very possible that our coefficient is what we would call bias and not really an accurate reflection. Okay? So another good example of this is if I have autism in organic food sales. I mean, if I had a data set like this, I mean, if I run a regression, this is a, definitely going to find a significant effect. It looks like these two things are moving identical, but I don't think anyone, if we ran the regression where autism rates were the Y variable and organic food sales were the X variable, I don't think anyone really thinks that organic food sales being higher is causing autism rates to be higher. It's more likely that these two things are being driven by a third variable that we haven't entered into the picture yet, that we haven't included as a control variable. So, maybe an emphasized focus on health is causing us to, see organic food sales go up, and it's also causing us to be more aware and see kind of this increase in autism diagnoses as well, right? So no one's would argue that this is causal. It's just that they're correlated because, right, Z, this other outside variable Z, is causing both X and Y to change, right? This increased emphasis on health is causing organic food sales and autism rates both to kind of be higher. So kind of this idea is that, I always like this little kind of, I don't know, cartoon or whatever. So I used to think correlation implied causation. Then I took a statistics class. Now I don't. Well, it sounds like the class helped. Well, maybe, right? Because taking the class, maybe there was an outside thing where it was more likely that I understand the difference and that I take a statistics class, like something else that I'm not taking into consideration, that Z variable is driving both of those, right? So, I put a slide on here. This is a very textbook way of like showing that if I run a simple regression, right? If I run a regression with only one variable and I'm omitting other important variables. So like, let's say the student athlete was this X1. If I omit in my regression something else that matters called X2, when I look at that coefficient estimate that I get from Excel, it will capture the true relationship, but also this additional component. Now, as soon as I include that SAT score variable, that X2 variable into my regression equation, I eliminate this biased component. So if I could include every possible variable that would impact GPAs on my right-hand side, then I would be perfectly capturing the relationship between every variable and GPA. But unless I include every important variable, I might have this bias that exists in my coefficients. Okay. So we kind of already went through this example with the student athletes and SAT scores, so I kind of jumped the gun on that. But going back, where are we at on time? Oh, we're great. So I want to talk about R squared here a little bit. So I'm not going to make you compute the R squared because Excel does it for us, right? But I want to try to give you some idea or intuition about what it's measuring. So if I were to look at kind of this guy right here, so I'm looking at the actual Y values, their difference from the average Y, so the deviation from the mean squared, then adding them all up. This should kind of look similar to like the variance, right? Here, what this is, capturing essentially the variation that exists in the actual Y variable, right? So this might be, the GPA variable I have in the data set. I could figure out what the variance is on it. I'm then going to, for every observation, come up with a predicted Y value. So based off of my regression equation, I'll use those coefficients and come up with a predicted Y value. And I'll show you how we do that here in a second. But if I look at the difference between those predicted Ys and the actual, the actual average Y value, this is kind of measuring the variation that exists in my predicted Y values. So if I take a ratio of these two, right, a ratio of these two, that's going to be what we're calling the R squared. So we're going to look at the variation that are in our predicted Ys divided by the variation that exists in the actual Y. And the way we can interpret this is it's how much of the variation in Y we're explaining with our X variables, right? With our variables that we used to make this prediction. So R squared is telling us how much of the variation in that Y variable we are able to explain with those X variables that we included in our regression. Now, one thing you can kind of think about this R squared when we look at in Excel, it's going to come in as like a proportion of the variation we explain. So, it's going to be somewhere between 0 and 1. Typically, we always then kind of just multiply it by 100 so that, R squared of 1,000, or sorry, 1,000, R squared of 100, right, represents, we're explaining 100% of that variation in Y. Okay? So just to kind of give you some examples of this, let's look at like that naive regression we had. So here the R squared is 0.008. So you'll notice there's a couple different R things in here. We're not going to go quite that far in this class into content, so you can kind of just focus on this R squared. Don't worry about multiple or adjusted R squareds. So we look at the R squared. We're explaining the proportion of the variation in GPAs that we're explaining with this student athlete variable is 0.008 or 0.8%, right? Move the decimal 2 places to kind of make it a percentage. So that's hardly explaining any of the variation. So what that's saying is, just using student athlete, my predictions that I'm coming up with, I don't see, I'm not explaining hardly any of the variation that exists in GPAs, right? Just a little bit. If I then include SAT scores, my R squared is now risen to almost 0.17. So now, using student athlete and SAT scores, I can explain about 17% of the variation that exists in college GPAs. So you can imagine, as I start to add in more variables, my R squared is going to get closer and closer to 100, because if I can include every variable that matters on the right-hand side, I will be explaining 100% of the variation that exists in Y. Because if I have every variable that matters, my predictions would be accurate, right? If I had everything that matters, there is no error term. Now, we can get close to 100% in practice. We're never going to get like an R squared of 100%, right? Or an R squared of 1, right? Because we can't capture everything. I mean, I'm sure there's something out there that they've been able to do that, but more often than not, we don't have enough data, or we don't have the right data to explain 100% of the variation in whatever we're trying to predict. Okay. If we then go to the kitchen sink variable, I've included a lot of other things now. You can kind of see, well, now I'm explaining about 30%. So it's getting better, but it's not great, right? I'm still somewhat low. So there's a lot of other factors that help predict college GPA, probably things like major choice or the university they're at, that we don't have information on. Okay. All right. Are there any questions over anything that I've kind of said, or just in general up to this point? Okay. So the next thing I want to do is kind of walk you through this idea of making predictions. So if I think about what I have here, I'm going to try to get this on one side. There we go. So my regression equation is, I'm trying to predict GPAs, and I've got this intercept plus coefficient on SAT plus the coefficient times student athlete plus high school rank. Oops, I forgot that coefficient. B3 times high school rank. Right? All these different variables in my equation that would allow me to predict GPA. So once I run this regression, and I have now the estimates for each one of these coefficients, right? If you then gave me a hypothetical person and was like, they had a 1,200 on the SAT score, not an athlete, 10th ranked in their high school, and you gave me all this information on them, I could then predict what their GPA is. So that's what I'm going to do. I'm going to show you a real easy way to set this up in Excel. So what I'm going to do is kind of think about this as, here's my hypothetical person. Right? So my hypothetical person, I'm going to say, well, I know that I'm always going to need to, well, I'll hold off on that. Let's say they have a 1,200 SAT, right? They are a student athlete. They were 12th ranked in their high school. And here's where I have to remind myself, I'm coming up with a hypothetical person. I think that these verbal math scores range between like 0 and 2. Yeah, so we'll say they got a verbal math score of I don't know, 0.9. Let's say they're female. They're not white, so we'll put they're black. We've got 55 credit hours that they've taken. The high school size variable, once again, this is like, I believe that they made it just so it was easier to see. So I think these represent like 9.4 would be, I think 940. So they scaled it. So I don't know, we'll just choose 4 point something as, you know, their high school size. So maybe like, I don't know, 450 kids, which would be 4.5 there, the way that that variable was input. So I now have this hypothetical person. I have a value for every variable. Well, now what I'm going to do is basically just plug things in this equation. Plug in all my coefficient estimates, right? I've got those here. And then plug in these hypothetical values for the different variables. So what I'm going to go through and do for each one is take the coefficient value and actually, so we can see this, I'm just going to delete these columns because we don't need them, so that you guys can see this easier. Sorry about that. I wasn't thinking that it was going to go that wide. So I'll delete these so we can see everything, right? So now I'm going to think about, I'm taking each coefficient, multiplying it by that x variable. Right? So take the coefficient, multiply it by this hypothetical person's value for x. I then want that to, you know, do that for every single variable. And then I'm going to add them all up. Now, one thing I don't want to forget to do is, well, the intercept always should be added in there as well. So when I look at the intercept here, I don't know, an easy way to do this would be put a 1 in here so that I'm just multiplying that coefficient by 1, right? I just want to add that coefficient in. Or if I don't want to do it that way, I could have just said, you know, make sure I add that coefficient in, that intercept coefficient. Now I'm just going to add them all up, and that should give me the predicted GPA for this hypothetical person, okay? So all I'm going to do is go through every single variable, use the coefficient, multiply it by this hypothetical person's value for x, and then add them all up. And don't forget to add in the intercept as well. Now, if I really wanted to, I could use these coefficients, and I could actually look at the actual data, and I could come up with predictions for every single one of these people, and then look at, okay, what's the difference between the actual GPA and the predicted GPA, right? I could do that for every single person. Now, why would I do that? I mean, that is actually one of the ways in which we calculate this part of the R squared, right? The predicted Y's minus the average Y, right? So we might want those predicted Y's for every single observation. So we can compute things like the R squared. Now, I'm not going to make you do it by hand. Excel's going to do all that work for us. But this idea of making predictions for a hypothetical person, that's useful, right? You know, and I could play around. Maybe they got like a, you know, it's a different person. They got a 1300 and they weren't a student athlete, right? And I start changing these things around. And I get different predicted GPAs. Okay. Any questions on that before we move on to the next thing? Okay with this? All right. Another thing that I might ask you to do on like the Excel, the 5th Excel or on the upcoming exam is not just come up with predictions, but determine which of these variables, right, that I've included as my independent variables, my X or my right-hand side variables, which of them can I say have a statistically significant relationship with GPA? And maybe I say statistically significant relationship at the 5% significance level, so my alpha is 0.05, okay? Well, I've got the p-value for each one of these. I could go through by, like just by hand and, okay, e to the negative, remember, anytime I say e to the negative, that's a 0, so, okay, 0 is less than 0.05, so I can reject the null for the intercept, or, right, remember, the null is that there's no relationship. So when I can reject that, I'm saying there's a statistically significant relationship. Well, the intercept, more often than not, right, is probably going to be significant in a lot of situations. So here, you know, we've got that. Usually we don't focus on the intercept too much. We focus on the variables we included as controls. So SAT score, we're rejecting the null. Excuse me. So there is a significant relationship between SAT scores and GPA. Student athlete is significant, high school rank. This verbal math score, well, 0.1 is not less than 0.05, so it's not, we cannot reject the null. So if we can't reject the null, we fail to reject the null, it could be that the relationship between this verbal math score and GPAs is actually 0. So we would say that we failed to reject or that we don't find a significant relationship between this verbal math score. Right? So really all we're doing to figure out which of these are significant at the 5% significance level, right, alpha of 0.05, is we're going through and checking to see is this p-value less than alpha. Well, you can do that by hand, but sometimes when you do that, you might look, oh, 1.4, that's a high p-value. Well, you're forgetting it's either the negative 20, it's basically a p-value of 0. But if we use that if statement that I've kind of been playing around with, showing you how to use, if I say, is the p-value less than this alpha that I've chosen? Comma, if it is, put in the word reject. If it's not, put in the word fail to reject. Right? So anytime I see the word reject, that's really telling me there is a significant relationship because I'm rejecting that the relationship is 0, right? That it's non-existent. And then anytime that this isn't true, I'm failing to reject, or I can't really say that there's a significant relationship. Now, when I copy this down, I want it to kind of update the p-value, but I need this alpha cell reference to stay the same, so yeah, make sure I freeze that. Okay. Now, when I copy this down, and if I double left click here, I'll kind of, went down a little bit too far there. Right. I'll kind of do this for each one of my variables, right? Comparing that p-value to alpha. So real quick, I can see, okay, the only, all these variables have a significant relationship with GPA except for the two in which I failed to reject the null. So what two would those be? Looks like whether or not the individual is white, so race doesn't really matter here in predicting GPAs, and then this verbal math score. So, if I'm in admissions or something and I'm, school's making everyone who enters take this verbal math score to try to help better predict what their, success will be, I'd look at them and say, yeah, I mean, this is a p-value that's close to being significant, but this isn't a very good test, right? If this is a good test, we should see that, like, there's definitely a relationship between it and GPAs, and apparently there's not here. We can't say that there's the relationship between these two, the slope coefficient is anything other than 0. We can't say that. We can't, because we failed to reject the null here. Okay. But using that if statement is a pretty easy way to do that quickly and not have to go through each one by hand and kind of eyeball it and compare. Okay. Any questions over anything that we just kind of did here? So we did some predictions. We made, determine what is significant at the 5% level. Any questions on anything related to that? Okay, so one thing I wanted to review is this idea of, let's go to an easier one. So let's say I was just using this naive 2 regression where I've just got SAT and student athlete. So here we could do predictions as well, right? So let's say I tell you someone's got a 1200 SAT score and they're not a student athlete. Well, basically what we could do is, well, it's just an equation, right? We've basically got an equation that we're just plugging things into. So I'm going to take the intercept, I'm going to add to that the coefficient on SAT times, they had a 1200 SAT, and then plus the coefficient on athlete, but we said they weren't an athlete, so times 0. Well, that kind of makes sense. If they're not an athlete, we shouldn't be adding that coefficient in. And that's how I would come up with a prediction for this individual. So just another example of kind of predicting that Y variable. What I could also ask you something like the impact of scoring 75 points higher on the SAT. Well, the interpretation of our slope coefficient on SAT is a 1 unit increase, so 1 more point. If I want to know the impact of 75 more points, and I think we did something like this last class, but I would just take 75. If I know the effect of 1 more point, the effect of 75 would be that times 75. Okay. So I could do this for other variables as well. I just want to kind of show you another example of that, making predictions. If I know the interpretation of my coefficient is the effect of 1 unit, finding the effect of more than 1 unit is simply, multiplying that by whatever number of units I'm interested in. Okay. Any other questions on anything there? Just got a little bit of extra time here. So one thing I did with my other section yesterday for next week's classes, I've got a bunch of different data sets, and I just want to go through more examples of linear regression stuff, just so we just get more practice. But I want to make sure you guys, like, I don't know, that whoever's tuning in to watch or kind of come to class is actually interested in what we're going over. So I'll get an announcement up, and I'll give some examples of some various data sets that I have. But if you just want to send me an email over the weekend or today about something that you kind of find interesting, and it's not for credit or points, it's just me trying to make sure that this stuff is interesting. Because, you know, to me, this linear regression, this is my, you know, favorite part of the class, in the sense that, like, this stuff is useful, right? Being able to pick up the relationship between these variables and GPA and make predictions. And, you know, if I see that, like, oh man, like some of these race identifiers have significant effects on GPA, like I might question, like, well, why? Like, is, you know, the university's not serving that, you know, whatever group it is, not serving them appropriately. Like, you know, it allows you to invest, like, figure out things that you should investigate into, because, you know, maybe there's discrimination, or, you know, maybe we can see that, oh man, heart attacks are, if we look at heart attacks and age, as people get older, heart attack rates are going up. Like, it allows us to figure out maybe where some issues lie. So I want to make sure that it's interesting to you as well. So send me an email, and that announcement will have different examples of data sets that I have as well. So one thing I'll kind of end today on, and I'll end it on this, and maybe some of you, I can kind of already see some people have already tuned out. So, but I think that this is interesting, and I won't expect it in this class, but I want to show it to you because it is powerful, and it is something we can do with regression to more accurately capture real world scenarios. So anytime I have a relationship between something, like I was before, we're really thinking about, we had like a linear relationship between things, right? Well, it's very possible that my data, right, the line of best fit is actually not linear, right? If I tried to draw a line of best fit that's linear here, I'm going to be making more errors than if I allow it to be non-linear, right? So, you know, if we go to like calculus and things, the way that we get an equation, or the way that we get a line that looks like this, is by not simply having y is equal to a plus b times x, we add in a squared term, right? But it's a squared term of the same x variable. So what we're going to do is basically do that with linear regression. So we can go to that data tab. I've got my college GPA is still my y variable. And now I'm just going to focus on SAT and SAT squared, right? So all I did was create another variable where I squared the SAT score variable. So I'll show you that here, right? All I did was square the SAT score variable for every observation. And I'll move this over. We'll call this non-linear. So what this would allow me to do is say, okay, is the relationship between GPA and SAT scores, you know, is it non-linear? So the idea there would be like, yeah, if I go from a 1100 to a 1200, maybe that's going to have a very different effect than if I go from a 15 to a 1600, right? Because once I get to a 1500 in SAT, I'm already like really, really smart. So, you know, anyone from, you know, 1500 or 1600, those two individuals, their GPAs are going to be very, very high. It doesn't really allow me to make a much better of a prediction. So maybe like different, you know, depending on what the SAT score is, a 1 unit change would be different, right? Going from a 1100 to 1101 might be different than going from a 1500 to a 1501. So this basically gives us coefficients, and here the p-values are, they're significant here. The square term is significant. So we can now use these coefficients, right? Plug them in, and then for different SAT scores, come up with a more accurate prediction of the GPA, because we now aren't forcing our predictions to be linear. Before, if you gave me an SAT score of 1200, my prediction was up here on this linear line. Now you can kind of see, if I allow to have this curve to this line, well, now my prediction using the squared term as well, I can come up with a prediction that's probably a little bit closer to where the actual data points are. So it's kind of a useful thing that we can do with linear regression. I see it pop up a lot because a lot of times the relationships between things we don't think are linear. You know, I'm an economics, so we always go back to, you know, thinking about price as a function of quantity, right? But the first unit is like, consumed. It has a lot more value than after I already have 100 units, the 101st unit. So we always think that like supply and demand curves have some curvature to them. We usually start out teaching it linear, but in practice they have curvature to them, and you could really pick that up using, some type of regression analysis as well. So pretty useful. Yeah, but I will end it there. We will pick up on Monday on some more just linear regression examples, and then Wednesday and Friday of next week, and then the Monday of finals week, I'll just be doing review, going through some of those practice problems, showing you some things that I think will be helpful as you're kind of preparing for the exam. And yeah, then we'll be at that finals week. So the end is near. So all right, well, enjoy your guys' weekend. I will see you on Monday. And I'll leave the Zoom open if anyone has any last minute questions.